Thank you, and welcome to the conference, and it's an honor and pleasure to me to be a first keynote speaker. There are two co-authors in this presentation, Dr. Mikhail from Sokolov Mathematical Institute, Moscow, and I would say that probably, so this is the man who contributed most to this topic. He started it about 40 years ago. Unfortunately, he was not able to come, though I still believe that probably it would have been more appropriate for him to make this presentation, because this is something new for me. I got excited about this subject about 3-4 years ago. And so I believe that, working with Nikolai Dalbilin, we revise some proofs, we make some new statement, and we have really nice agenda what to do in this area. And so recently it became very, very popular, probably first and foremost in connection with development of quasi-crystals. Almost every month, we have some requests to come and present on this subject. So maybe you also become interested in this. Okay. And probably every other slide, you're going to hear the name of Boris Delaunay. Boris Delaunay was a founder of this area. And it happened that this year is 125th anniversary of his birthday, and so we're going to have conference in Texas devoted his memory, then a couple conferences in Moscow. But I thought it was absolutely appropriate to devote this talk to him, because as I said, probably on every other slide I'm going to mention his name, Delaunay, because of his contribution to the area. Okay, so I'm going to talk about crystals, natural crystals, and mathematical model of crystals. So in this picture, you see a beautiful crystal zeolite. And so why it looks so nice? Because the structure of crystals is very, very interesting. It's really well ordered and so periodic. On the right side, you see the model of atomic structure of zeolites. And if you look at this model, probably you will not notice any periodicity here or any kind of really clearly defined global order. It looks like more like Fuller-N. Actually, it's not. So in the next slide, you'll see natrium chlor. So this is the left side, the model of natrium chlor. And over here, you already see some structure, lattice structure, red balls and white balls. And it's absolutely clear from this picture that so natrium chlor atoms are at the nodes of some lattice. And this is model of cubic lattice for natrium chlor. Okay, so over here, we try to formulate postulates or physicists' beliefs. So as it perceived by mathematicians. So let's put it this way. I cannot claim, so this is exactly what physicists believe in, but reading their books, Feynman lectures and other literature, we found a lot of evidence, so the perception of crystals, something like this. And so if you look at the first one, solid crystal formed from amorphous solution, melt or gas, so that's fine. It's clear physical statement, probably it's true, they know better. Under certain physical conditions, temperature, pressure, atoms have a tendency, to collect themselves into small groups or self-assemble. And this is very interesting process from a mathematical point of view. Still a lot of things to do, to understand from the perspective, not of physicists, mathematicians, what's going on over here. And this is one of our items of agenda for research. Then, so number 3 and number 4 are extremely important from the point of view of physicists and mathematicians. So the assumption is that atoms of the same kind self-assemble in the similar clusters irrespective of their place in space. So it looks like unreasonable if atoms are about the same, then it does not matter where they are. They self-assemble into the atomic structure. And the repeatedness of the atomic structure automatically implies periodicity. And this is very, very questionable statement. However, if you read literature in physics with this respect, you will see immediate jump from number 3 to number 4. with no argumentation. So this is just belief, because atoms assemble themselves in the same matter irrespective of space. Then so periodicity exists. So just to support my claim about previous slide, so we listed the Feynman quote, when the atoms of matter are not moving around very much, they get stuck together and array themselves in a configuration with a low energy as possible. If the atoms in certain place have found a pattern which seems to be low energy, then the atoms somewhere else will probably make the same arrangement. For these reasons, we have in a solid material repetitive pattern of atoms. It's okay to have repetitive pattern of atoms. However, immediately after that, say Feynman in his books, so he considered atoms as lattice, as pure periodic, and probably for some time, nobody questioned the kind of assumption. And to prove this is true or not was perceived like pure mathematical exercise. Of course, mathematicians can do whatever they want to do, but it's true whether they can prove it or they cannot prove it. Okay, but the situation changed dramatically in mid-70s when Penrose discovered or rediscovered, because if you look in some Arabic, patterns, probably you can find something like Penrose mosaic, something like this that's called Penrose mosaic, right? And this is Penrose himself, and this is Penrose mosaic, actually, by the way. So it just happened to be there, right? So if you look at this picture, right, it looks then, so yes, it's about the same everywhere, right? And therefore, probably it should be periodic. It should repeat themselves over infinitely many times. Yes and no. So look, if you take every patch in this picture, you can move this patch around so infinitely many times. However, so this structure is not periodic. You cannot move the entire picture such that it will be exactly the same picture. So this became a shock, I would say, for first and foremost physicists. Mathematicians said, of course it should be this way. But for physicists, it was big surprise. But it was fine for probably 5 years, right? They said, look, it exists only in theory or in some pictures. It cannot exist in nature, but it happened to be absolutely wrong when Shachtman obtained some substance with 5-fold symmetry diffraction that is not possible in crystals. Probably, the story of Shachtman discovery deserves special lecture, maybe half hour long at least, But it's very exciting, Physicist was completely in denial about this fact. Probably they were in denial for 15 years, right? So probably for Shachtman, it was very difficult period of his life. However, he was awarded in 2011 a Nobel Prize in chemistry because of this discovery. And after that, so it became a natural question. So if you have local pattern that looks the same, does it mean that matter will be periodic or not? And basically, that's is our theory about. So this is local theory for crystals. So what we're trying to do, we're trying to find answer to 2-3 questions. Is attempt to find the answer, what kind of local identity it should be. So how big, a piece of matter or matter in mathematical point of view, you need to take with certain conditions to guarantee periodicity, right, or kind of periodicity. And then you define a crystal with other concepts that describe the global order and periodicity. Of course, if you say that it's periodic, it will be periodic. But how to take a small piece, right, give some condition on this small piece, and after that, claim so the entire structure is periodic. So this is local theory of crystals. So this is the subject, and that's what we're trying to do. And unfortunately, the results is very hard to obtain. That's why, I was took a liberty, to say history and so perspective there. So whenever you have about any science, probably it's impossible to make presentations for 20 minutes about development of this science for the last 60 years. It's possible, kind of possible in this particular matter, because it's very, very difficult to obtain new results. And I'm going to show you with the new results. But before that, I need to share some concepts that we operate with. Okay, first of all, as I said, the Launay set. The Launay set is mathematical concept that describe matter. So any matter. For quite some time, so people believe so the Launay set so describes any matter. It's happened to be a little bit more general. Then the concept of lattice describe periodicity. It was discovered probably by Lagrange in late 18. However, it started using in crystallography by Gauss in 1810, and then late 18th century by Gauss. Early 19th century by Gauss. Then regular set, so this is generalization of the concept of lattice that explicitly does not include periodicity, however, try to describe some substance that look like periodic. And so it was introduced in 1885 by Fedorov. Then crystal generalization of the concept of regular point set to describe the atomic structure of an ideal monocrystal. Again, ideal monocrystal is kind of mathematical concept that I'm going to talk about. It was 85, 89 Fedorov. And finally, crystallography group, mathematical concept to describe the global order in the internal atomic structure, 89, 92 Fedorov, Schoenflies. And so Fedorov believed that he proved a lot about crystallography group. It happened to be not true. It was mistakes in his proofs. However, Schoenflies did it right. Okay. So definitions. First of all, what Delaunay said. Delaunay said, generally speaking, there's some points that is not very close to each other everywhere, and then so there is no big holes in the matter. So basically that means, that so the distance between any 2 points, no more than 2 are small, right? So they cannot get very close to each other. And so whatever place you take, so there is no huge hole. Basically that means that so whatever point in space you take, there is some point of Delaunay space on the distance r capital. Okay? As I said, probably in 30s and 40s, people believe so this is the mathematical concept to describe a matter. It's too general. Then regular set, and from this, maybe regular set, I kind of commented a little bit on perception of Gilbert and Van Cohen in this respect. When they're trying to describe regular set, what they said, assume, you stay in the point and look around, right? Whatever you see, then you move to the next point, and you'll see exactly the same picture. So this is the concept of regular set. A regular set. However, if you use mathematical concept to give the definition, that means that a group of isometries act transitively on this set. And so a very useful concept is orbit with the group G of X is all images of any point X. Okay. Fundamental domain is extremely important to describe a crystallography group. And so we call fundamental domain such that so first of all, it's discrete. That means that G of X is discrete space for any point X. And intersection of f of G and the orbit is not empty. And for any point X, the interior of f of G contains no more than 1 point. Crystallography group, as I said, the most important concept is definition G is discrete subgroup and fundamental domain is compact. So over here I give 2 examples. Say if you take group that generated by rotation by angle 2 pi over n, right? So then a domain, fundamental domain will be angle. So the entire angle. And therefore it's not bounded, and therefore this group is not crystallographic group. But at the same time, if you take Z to the D, so this is crystal again. So if you take lattice, right, then you know, depending what kind of group you have, if you have pure moves, then fundamental domain will be all squares. You have all reflection that preserve order, then fundamental domain will be a quarter of a square, any quarter of a square. Okay, so a set is regular set. This is his theorem if and only if there is crystallographic group G such that X is orbit of X is orbit respective to this group. And over here I have actually some picture. So again, so my group is this lattice, and therefore in my group actually I can move and I can rotate by 90 degrees or 180 degrees. And then if you take any point, right, and then what is G of X? Whatever we have red points over here, this is G of X. And therefore I just want to draw attention that nodes of the lattice itself do not belong in this particular case for G of X. However, immediately you have 4 lattices instead of 1. And therefore, G of X in this case is 4 lattices. Okay. Crystal is the union of G of X sub naught, where X sub naught is finite set of points, and G is crystallographic group. So this picture, look, if I have the same, G the same, orientation preserving lattice, you know, so you have parallel moves or rotations by either by 180 degrees around some points or by 90 degrees about some points. And then if you take any one red point and apply this group, you have all red points. If you have any green point and apply this group, you have all green points, right? And then if you have take nodes themselves, right, then you have only nodes, so nothing will change. So this is example when you have 4 lattices and all have non-congruent and parallel lattices. This is example of crystal. Okay, probably I'm going to skip this one. So what I need to do, I need to define a cluster, and cluster is kind of ball, but you know, the ball that contains only points from my set X. And therefore, if you take any open ball with radius r and take only points from my set, so this is the cluster. So then you know definition of identical cluster. Basically, there is group of symmetry that move one cluster to another. And after that, you know, all clusters will be splitted into the group of equivalencies. And basically, so if we want to find out in what case we have a finite number of this group of equivalencies, in what case we have infinite number. So the last set is finite type if we have only finite number of classes for the radius 2r. And then the last set is crystal if and only if the function that defines the number of classes that depends on rho is bounded above function. So examples over here are crystals. Okay, then probably I'm going to skip some technical definitions. And so there is a local, so pure, kind of really good example of a local theorem. So after these conditions, such that so there is only cluster of one type for rho plus r, for rho plus 2r, and then if you take group of symmetries with the same radius rho and with radius rho plus 2r, the group of symmetries will be exactly the same. In this particular case, then okay, thank you. In this particular case, you have a regular set. But it looks like so this condition a little bit too technical. So who is going to find this number rho? Who is going to find to check whether the group stays the same? Therefore, in the best case scenario, we need conditions like this. Look, in dimension 2, n and 4r is equal 1, implies X is a regular set. And in dimension 3, n equals 10r equals 1 implies X is a regular set. That's kind of theorem that we need to obtain, so to have really good example, so really good theory for physicists. In this particular case, so 4r cannot be improved. You cannot take number smaller. And so here is my picture how you can do it, so how you can prove that in two-dimensional space, in any dimensional space, you cannot take number 4. If you take this kind of lattice, with long rectangles, and so naturally, R, this is R, you take 4R, and then you shift this lattice a little bit. So you can shift it in infinitely many ways, of course. So this stays the same, they shift it to the right, this shifted to the left. So you have a continuum number of shifts, and only 4 of the shifts actually give you a regular set. All other will give you an irregular set. However, the condition for n of 4r equals 1 happen to be true. Okay. So that's where, okay. That's why, so what we decided to do, we decided to take a smaller class than all the linear sets. And for example, if you set all symmetric, then basically all symmetric set about any point will give you a crystal. If you have kind of opposite example, so when around each point, so if you take center symmetric, the point does not belong, then 4r is sufficient to have a regular set. And so this is to any local antipodal linear set is crystal. That's what I'm saying here. Then this is, again, a very important technical theorem. It takes about 5 pages to prove. So, but with help of this theorem, you can obtain really nice results. And probably I'm going to skip all the stuff for next presentation, right? So I would like to have summary. The local theory establishes connection between the local structure and the global order in periodicity in crystal. So it's possible to have some local conditions that guarantee periodicity. Then it's possible to determine, so what is the largest radius you have to take even for two-dimensional space. Of course, 10R looks, even for three-dimensional space, way too big of a number. So we strongly believe that, say 4R is also sufficient for three-dimensional space. But of course, if you go to higher dimension, that probably this number will be a little bit larger. So the bottom line is the technique that we have been using right now so far does not allow us to refine these numbers and obtain kind of small numbers. And this problem, as I said, became very, very important in relation to quasi-crystals. I am talking here only about crystals. If you start doing quasi-crystals, so this kind of nightmare over there, it's very interesting questions, very natural questions, very important for chemistry, for physicists, but so not much you can do, not much has been done in the terms, from the point of view of mathematics. And then, the next, our direction to move, not to take Euclidean distance, but, maybe define some kinds of distance that will give different results. Not to take the entire group of isometries, maybe to take some subgroups of isometries. And that's how maybe obtain better result. Probably I can stop here for two reasons. First of all, that's how I have time to answer questions, if any. And then we'll have time to prepare for next presentation.